In this video, we'll be going over topic 3, work, energy, and power. So let's start off with what energy is. It's the ability to do work and is measured in joules. Work is how energy is transferred, and 4.19 joules is equal to 1 calorie, which is the conversion rate. And the definition of work is that it's the scalar dot product between force and displacement. What you need to know is that when a force is applied, the object must move. And therefore the only parallel component of force will contribute to the movement. So the formula for work is force times displacement times the angle between the force and displacement. So you need to measure that angle so that you can calculate work. Now for the scalar dot product, you need to know that the scalar, it has no direction, and these will include work and energy. And the dot product is that cosine is going to be essentially the constraint for this equation. And remember that only the force parallel to displacement does work. So you need to know a little bit of trig, but these are essentially it. So at 0 degrees, the result is max work. So the reason is because cosine, let's write this like this. So cosine of 0 degrees, this is just think of the unit circle right here. Cosine of 0 degrees is just 1. At 0 degrees, the x value is going to be 1. And then now that our next values, at 90 degrees, you're going to have 0 work. And then at 180 degrees, you have negative work. So this is essentially doing the trig in your head. So it's cosine of the angle between, because this is equal to 0 and this is equal to negative 1. Negative 1, 1, and 0. So cosine is essentially x. So you're looking at the x coordinate at that degree, and what x coordinate are you at, basically. And negative work, you need to know that this doesn't mean direction, because remember that it's a scalar. Work is a scalar. So this means that energy is removed, not relating to direction, because remember, scalars have no direction. And that okay, now let's move on to our next concept. So work done by specific forces. Well, so we have first of all, we have the normal force. And remember that it's always perpendicular to motion. So we'll represent that as Wn is equal to 0. And now we have friction. And friction is always gonna do negative work, because remember, friction always opposes the direction of motion. So basically it's always gonna move it backwards, basically, like whatever is moving forward, friction is going to be going in the opposite direction, making it go back. And what friction does, it essentially converts mechanical energy into thermal energy. And the relationship that we represent this work done by friction by is negative friction K. So that's kinetic. That's in motion, not static, times D. So what you need to remember is that negative work, again, does not indicate direction, because work is a scalar for friction. And let's move on to gravity. So gravity, it can can do positive or negative work. And this depends on direction of motion. So for example, like what this means by positive or negative work is that it can either be an aid, or deter, I guess. So basically think of like when you're throwing a ball, throw a ball. So when you throw a ball in the air, remember gravity is down, right? So like because gravity is like pushing down, let's say you throw a ball and then you throw it up, right? So gravity is gonna make gravity just like orange. So gravity is always gonna be going down, and because it's always going down, this is going against the motion, so it's doing negative work. But here, if the ball is falling down, it's doing positive work because the ball is going down and it's like going in the same, this is like opposite motion, and then this is same direction of motion. So it's essentially aiding or deterring, and that's what it means basically. So yeah. So now let's talk about path, independence, and also conservative forces. So what this means is that something you need to know is that the work gravity does is path independent. So what this means is that only initial and final heights matter. So this means that on a closed path, zero work is done. So again, now let's talk about conservative and non-conservative forces that we just talked about. Conservative forces. So this is going to be gravity. And then as our non-conservative force, we have friction forces. Because think about it, like some energy is lost. You can think like, kind of remember it like that, like energy is lost in like the form of like the system. It's like lost to the environment because it's thermal energy, and like friction, it depends on path. And remember that if friction is present, that means mechanical energy isn't conserved. Now let's move on to, so again, what you need to remember about like friction being a non-conservative force is that work, it depends on path taken. So it's path dependent, and path taken, and friction, it is path dependent, so it dissipates mechanical energy as heat usually, and this is unrecoverable as usable work. So this means the process is irreversible. So it's removing energy from the system. And you can't get that. Like, for example, like you cannot get that energy back by reversing the direction. So it's literally, you can't get it back after you exerted that friction. So let's move on to mechanical energy and conservation. Mechanical energy and conservation. So remember that mechanical energy is represented as E is equal to kinetic energy plus U, and that gravitational potential energy is the formula U equals to mgh. And remember that the height is going to be measured from a reference level, and that it only changes matter. And remember, kinetic energy is K is equal to 1/2 mv squared. And remember that conservation of energy is gonna be E is equal to A, EA is equal to EB if non-conservative forces are only present. So let's talk about the pendulum energy problem. So this is a formula you have to remember. H is equal to L minus L cosine theta. So let's draw what a pendulum is. So a pendulum is basically like you have this ball, and then there's this thing, it's like swinging around like back and forth. And this is the frictionless pivot. This is the amplitude. This is the massless rod. It's negligible. And that's the ball. And then this is the trajectory. It's like basically a curve like this. The ball just goes back and forth. Now, the force of gravity is going to go down like this. And this is the angle. Amplitude is basically relative to pendulum at rest. And up here, there's potential energy when it's like up here, but then when it's like here, this is the max kinetic energy. And basically just goes back and forth. Now, let's talk about the energy equation used. It's going to be mgh is equal to 1/2 mv squared. And then we can notice that the mass cancels here. So then we have gh is equal to 1/2 v squared. This is a classic setup for problems. Now let's talk about power. So power, let's derive this. So P average is going to equal to work over time. And we know that work is defined as F cosine theta. So then we can divide that by T, and then we can rearrange this for P average is equal to F cosine theta V average. And then this is the general form that instantaneous power can be calculated. So we have P instantaneous is going to be equal to F cosine V, which in vector notation is the scalar product. So that's just rewriting that as just P is equal to F dot V. Now let's talk about the units. So a watt is going to be joules over second. A watt is going to be also equal to volts times amps. and a kilowatt is equal to this expression, kVA squared minus kVAR squared. And you can convert watts to kilowatts by dividing wattage by 1,000 as per the root. So power is equal to work over time, and it's in units of 1 watt is equal to this unit right here. That, or you could also use the alternative power formula, which is P is equal to FV, and this is use this when force is parallel to velocity, and also when you have constant speed. Now let's do some practice problems. So let's say that we have a 5.0 kilogram box pulled 10 meters across a horizontal floor by a 30 Newton force applied at 40 degrees. And let's say the coefficient of friction is 0.25. So let's draw this out really quickly. We have the box right here, and then it's pulled. So we'll make this just that's just a reference. This is this, and we have 30 newtons. This is our 5.0 kilogram box. This is gonna be 40 degrees. And the floor, the friction, is going to be in the opposite direction. And it's going to be smaller than that because it's still moving forward. So that means that friction has to be smaller. We know mu k is 0.25. Fk is basically going that way. And this is Fa. Now, let's find the net work done on crate. So let's set this up. First, we have to find the work by Fa, the applied force. So Wf is going to equal to Fd cosine theta. Wf is going to equal to 30 times 10 times cosine of 40 degrees. This is going to simplify to 300 times 0.766, and this is going to simplify to 229.8 joules. Now let's find the friction force. So friction, we have that N is the normal force. Draw this. The Fn is going to be equal to Fg, and we know that Fg is equal to mass times gravity. So therefore, and we also know that the box is only moving in, box is at vertical equilibrium because the box is only moving to the side. So that means that it's neutral. Everything cancels out in the vertical directions. So that means that you can set them equal to each other by saying that Fy is equal to N. So N is going to be going up, and then Mg is going down. So then rearranging that, we have that N is equal to Mg by adding Mg to the other side. So then we can plug in 5.0 times 9.8, and then that's going to be equal to 49 newtons. Now we have Fk is equal to the coefficient of friction, K, and this is going to be equal to 0.25 times 49, and that's equal to 12.25 newtons. And now let's find the work by friction. In order to calculate this, we have WF is equal to negative FKD, which we had on our formula sheet earlier. When this is going to be, we just calculated this, negative 12.25 times 10, and that's equal to negative 122.5 joules. Now we had to find the net work. Now we had to take our work up here, we found, and then subtract it from this. Subtract that from this. So this minus, we have the work done by FA minus work done by friction, and you subtract because smaller. Your work is always, well, work won't always be positive, but we can just do it that way. That's gonna be work net is equal to 107.3 joules. Now let's do our second problem. It's gonna be on path independence of gravity. So what this means, okay, so we have a 3.0 kilogram object that moves from 1 meter to 6.0 meters above the ground. So we want to find the work done by gravity, and also we want to find out, would the work change if the object followed a curved path? So think about path dependence or not. So the object moves from 1.0 meters, so the object is like here. This is the ground. 1.0 meters, and then it goes up here. So this is like 6.0 meters. Now we have work done by gravity. This is going to equal to mg times y initial minus y final. So work done by gravity is going to, plugging everything in, that's 3.0 times 9.8 times 1.0 minus 6.0. And then that's just going to equal to negative 147 joules. Now, this is a question, would the work change if the object followed a curved path? Well, no. Because the only force is just gravity. Because we aren't mentioning like air resistance or anything. So we know that gravity is conservative and path independent. So like changing it to a curved path wouldn't do anything to the amount of work done, because it would be the same. Now let's say we have a question about pendulums and geometry. So let's say we have a pendulum of length 2.5 meters is released from rest at 35 degrees. So we want to find the speed at the bottom. So first, let's find the height. Now, we know that the pendulum is like this. Pendulum is up here. We have this. We have the ball right here. So it's a pendulum of length 2.5. Assuming that's like 2.5. And then this is at 35 degrees. And we let it go. So we're trying to find the height. So for the height, we know that height is going to be the formula L minus L cosine of theta. We know that h is the length is going to be 2.5 minus 2.5 times cosine of 35 degrees, which is the angle over there. So that's just going to simplify to 2.5 minus 2.05, and h is equal to 0.45 meters. Now we have to do some energy conservation. So because we know that mgh is equal to 1/2, or because we know that mass cancels out, so we just have gh is equal to 1/2 v squared. So then we can just solve for v by multiplying both sides by 2 and also taking the root. So yeah, so we have v squared is equal to 2 times 9.8 times 0.45, and then we have v is equal to square root of 8.82. So v is just equal to 2.97 meters per second. Great, so now let's do a problem on power at a constant speed. So let's say we have a motor that pulls a sled at a constant, so weird ass, constant speed of 6.0 meters per second using a horizontal force of 800 newtons. So let's just draw this out. We have this, and we have the sled, and this is 6.0 meters per second. That's the velocity with 800 newtons FA. And we want to calculate the power output, and also let's also calculate the time required to do 96,000 joules of work. So we have, for this, we can use the alternative formula for power, which is P equals FV, and that's going to be 800 times 6.0, and that's equal to 4,800 watts. Now for B, we just have P is equal to W over T. Now we want to get the time, so we're just rearrange that by multiplying both sides by time, and then that cancels out. So then we have time is equal to, time. And then we divide both sides by P again. And then time is equal to work over power. And then we have T is equal to 96,000 over 4,800. And then T is equal to 20 seconds. Okay, thanks for watching.